Your smartphone determines your position within a 3-meter accuracy. It works like magic until the sun decides to intervene. In May 2024, a series of massive solar flares erupted. High-energy X-ray and ultraviolet radiation reached Earth in just 8 minutes, instantly ionizing the lower atmosphere and causing a shortwave radio blackout on the daylight side of the planet. But for satellite navigation, this was merely a prelude. Shortly after, the Sun unleashed a coronal mass ejection, a gargantuan cloud of magnetized plasma that took nearly 2 days to reach our planet. The physics capable of destabilizing your navigator accelerates during these exact moments, though the layer itself is always at work. This layer is the ionosphere, with its peak density residing between 200 and 400 kilometers above Earth. Solar radiation strips electrons from gas molecules, creating a layer of charged particles. When a GPS satellite transmits a signal from orbit, it must pass through this plasma fog. And plasma is not a vacuum. It acts as an obstruction, slowing down radio waves. This delay is calculable. On quiet days, our systems handle it seamlessly. But during a severe geomagnetic storm, the balance shatters. It all comes down to total electron content, TEC. Imagine a column of air 1 square meter in area, extending through the ionosphere into space. We count the free electrons within it. On a clean day, this count is minimal. But when a solar plasma cloud slams into the planet, the density of charged particles surges tenfold. This is not a storm in the terrestrial sense. This is an invisible geomagnetic disturbance literally agitating Earth's magnetic field. For a GPS signal, this space turbulence acts like frosted, rapidly flowing glass. The delay is bound by a strict physical formula. At the primary civilian frequency, every 10 units of electron density add more than 1.5 meters of ranging error. Your phone cannot calculate this on the fly. Instead, it relies on a built-in correction model. Just 8 digital parameters are tasked with describing the state of the entire planet's ionosphere. Furthermore, this baseline data is updated from orbit only once a day and is strictly designed for a stable atmosphere. When the atmosphere shifts rapidly, the model becomes obsolete instantly. The algorithm operates on outdated parameters and the error compounds. In May 2024, during the most severe disruption in 2 decades, positioning errors reached 70 meters. The problem isn't the math, the problem is the model itself. The geomagnetic storm of May 2024, a G5 category event, became our benchmark case. The KP Activity Index hit its maximum of 9, a level unseen since the famous Halloween events of 2003. Positioning errors of 10 meters or more were recorded across the United States. But GPS is not just about coordinates. It is, first and foremost, about time. Global financial exchanges synchronize millions of high-frequency transactions using atomic clocks on the satellites. Power grids balance substation loads based on these identical timestamps. 5G base stations require nanosecond synchronization to function as a unified orchestra. During severe storms, this timing rhythm degrades. Critical terrestrial infrastructure utilizes ground-based backup atomic clocks operating in holdover mode. Yet, without satellite cross-checks, their precision inevitably drifts over time. If the disruption prolongs, systems begin to desynchronize. Farmers in the US have already experienced this firsthand. At the peak of the storm, their high-precision GPS-guided tractors lost tracking, halting planting operations and costing the industry hundreds of millions of dollars. We have built a civilization that depends on signals from orbit far more than we realize. Aviation does not rely on luck. Systems are fundamentally designed with the assumption that GPS performance can degrade. Pilots receive real-time space weather alerts and can navigate via ground-based VOR and DME beacons. This frequency range is significantly more resilient to ionospheric anomalies than shortwave bands. There are also completely autonomous inertial navigation systems, INS. They do not look at the sky at all. Modern ring laser gyroscopes measure the aircraft's physical movement. The drift rate of standard commercial systems from Honeywell accumulates at roughly 1 nautical mile per hour of flight. After a transatlantic crossing, this results in an error of several miles. Yet it is entirely sufficient to safely maintain course until the aircraft connects with ground beacons for correction. During extreme storms, dispatchers and airlines actively reroute flights away from polar zones to mitigate the risk of communication loss caused by polar cap absorption. This isn't panic, it is risk management. This is not a navigation problem. This is a single point of failure problem. GPS is accurate only until the moment it isn't. The ionosphere does not negotiate. Subscribe to systems, not to stories.